Right now, while you're watching this, the moon is quietly pulling away from us. Not fast enough to notice in your lifetime, but fast enough that scientists have measured it, tracked it, and confirmed it happens every single year without fail. Every year, our moon drifts about 3.8 centimeters further from Earth, roughly the width of your thumb. It sounds small. It isn't. Over enough time, that tiny drift rewrites the rules of our entire sky, ends a phenomenon that has shaped human history and mythology for thousands of years, and eventually leaves Earth spinning in a way it has never spun before. The moon didn't start out as our neighbor by choice. It was born from violence. The collision of two young worlds so catastrophic, it reshaped the surface of our entire planet. And ever since that moment, over 4.5 billion years ago, it has been slowly, patiently drifting away from the very planet that created it. I'm going to walk you through exactly how the moon was born, why it's leaving, what's hiding beneath its cratered skin, and why the countdown on our current sky might be shorter than you'd expect. Welcome back to Big Data Vault. This is the real story of the object hanging above your head tonight. Before we begin, if you're curious about the universe and the incredible stories hidden within it, consider liking the video and subscribing. Every bit of support helps us bring more fascinating discoveries to curious minds around the world. Now, let's begin. To understand where the moon is going, you first need to understand where it came from. And the story of its birth is more violent than almost anything else in our solar system's history. The leading explanation for the moon's origin is known as the giant impact hypothesis. Roughly 4.5 billion years ago, when Earth was still a young, half-formed planet, a Mars-sized world, often nicknamed Theia, slammed into it. This wasn't a scrape or a graze. This was a full planet collision, violent enough to melt and vaporize enormous portions of both worlds. In the chaos that followed, a ring of debris was blasted into orbit around the newly wounded Earth. Molten rock, vaporized crust, and fragments of both planets, all swirling together in a disk of destruction. Gravity did what gravity always does. That debris disk began pulling itself together almost immediately, clumping into larger and larger fragments. Current models suggest the moon itself may have physically assembled out of this disk in as little as a few decades to a century. An almost unbelievably fast birth on cosmic timescales. But being assembled and being finished are two different things. What emerged from that rapid accretion was a fully molten sphere of rock, and it would take roughly another 100 million years of gradual cooling before that global ocean of magma fully crystallized into a solid body, the moon we recognize today. We know this story isn't just a good guess because of one piece of extraordinary evidence. When scientists analyzed the rock samples astronauts physically carried back from the lunar surface during the Apollo missions, they found something remarkable. The chemical fingerprint of moon rock is nearly identical to the chemical fingerprint of Earth rock. Not similar the way two planets in the same solar system might coincidentally resemble each other. Nearly identical, the way two pieces of the same shattered plate match when you hold them back together. The moon isn't just Earth's neighbor. In a very real sense, the moon is made of Earth. And ever since that fiery birth, an invisible tug-of-war has been playing out between Earth and its child, a relationship defined by gravity, tides, and a slow, inevitable separation that's been unfolding for billions of years and is still happening today. That's the open question this video is going to answer. If the moon was born locked in Earth's gravity, why is it now slowly slipping away? And what happens when it finally reaches wherever it's going? You'd assume that a moon locked in orbit around Earth for 4.5 billion years would have settled by now into a stable, permanent distance, the same way a planet settles into a stable orbit around its star. That's the intuitive picture most of us carry around. It's wrong, and the reason it's wrong comes down to something you can observe on any beach on Earth: the tides. Here's the twist. The moon's gravity doesn't just pull on solid rock. It pulls on Earth's oceans too, dragging a bulge of water toward itself as it orbits. But Earth rotates faster than the moon orbits, which means our planet's spin actually drags that tidal bulge slightly ahead of the moon's position, rather than keeping it perfectly aligned. That slightly ahead bulge exerts a tiny gravitational tug of its own, forward in the direction of the moon's orbit, very gently accelerating the moon and nudging it into a very slightly higher, wider orbit. Think of it like a child on a swing, being pushed just a fraction of a second before they reach the perfect point in their arc. That small mistiming doesn't stop the swing. It actually adds a tiny bit of extra energy to it, sending it slightly higher each time. Earth's oceans are doing exactly that to the moon, on a truly enormous scale, one imperceptible push at a time, for billions of years running. The payoff of all that pushing, 3.8 centimeters of extra distance every single year, measured with extraordinary precision using laser reflectors that Apollo astronauts left on the lunar surface decades ago. Scientists on Earth still bounce laser beams off those exact same mirrors today, timing the return trip to calculate the moon's distance down to fractions of an inch. Here's something you'd think should be a coincidence, but isn't. The moon takes exactly 27.3 days to complete one full orbit around Earth. And it also takes exactly 27.3 days to complete one full rotation on its own axis. Those two numbers matching perfectly is not chance. It's the result of the same tidal forces responsible for the moon's slow drift, acting over billions of years to lock the moon's rotation to its orbit. This is called synchronous rotation, or tidal locking, and it's the reason we only ever see one face of the moon from Earth, the same familiar patchwork of craters and dark plains, night after night, for the entire span of recorded human history. Picture two dancers spinning slowly together, arms locked, each always facing the other, no matter how the pair rotates across the floor. That's essentially the choreography Earth and the moon have settled into. The moon isn't frozen in place. It's still rotating. It's simply rotating at exactly the same rate it orbits. So from our perspective, it always shows us the same face. Now here's the part that surprises people. This doesn't mean the far side of the moon is some permanently dark, mysterious realm, the way pop culture sometimes imagines it. The far side gets just as much sunlight as the near side. It simply gets that sunlight at different points in the lunar cycle. During what we call a new moon here on Earth, when the side facing us is dark, the far side is having its full daylight. It's not the dark side. It's simply the side we never get to look at directly from home. You'd expect both hemispheres of a tidally locked moon to look roughly the same, since they're made of the same original material and shaped by the same history. Wrong again. And this mismatch has puzzled scientists for decades. The near side of the moon, the one we've stared at for all of human history, is covered in large, dark, smooth patches called maria, Latin for seas, even though there's never been a drop of liquid water in them. These are ancient basaltic lava fields, formed when massive asteroid impacts billions of years ago cracked open the lunar crust deeply enough that molten rock from beneath could flood upward and fill the resulting basins, cooling into the dark plains we still see with the naked eye tonight. The far side tells an almost completely different story. It has almost none of these dark maria. Instead, it's overwhelmingly covered in pale, ancient, heavily cratered highland terrain. A landscape that looks in places more like the surface of Mercury than like its own near-side twin. Scientists still don't have a fully settled explanation for why one side of the moon experienced so much more volcanic flooding than the other, though leading theories point to a thicker crust on the far side, made more resistant to rupture by the extra heat it absorbed from Earth throughout its early molten history. It's a genuine unsolved mystery hiding on an object we've been staring at every single night of our lives. You'd think, given everything we've learned about the moon's dramatic birth and ongoing tidal relationship with Earth, that it must have picked up at least some kind of atmosphere over 4.5 billion years. It hasn't. And the reason cuts right to one of gravity's most brutal rules. The moon does technically have something resembling an atmosphere, called an exosphere. An extraordinarily thin haze of trace gases like argon, helium, and neon. But it's so sparse that its surface pressure is, for practical purposes, indistinguishable from the vacuum of space itself. The moon's gravity, at roughly 1/6 of Earth's, simply isn't strong enough to hold onto gas molecules long term. They drift off into space almost as quickly as they might arrive. Imagine trying to keep a cloud of balloons tethered to the ground using nothing but a few pieces of thread. A light breeze, and they're gone. That's essentially the moon's relationship with any gas that tries to settle on it. Without a strong enough gravitational thread, nothing sticks around. The payoff of this thin, practically non-existent atmosphere is brutal. With nothing to trap heat or block radiation, the lunar surface swings between roughly 127 degrees Celsius in direct daylight and minus 173 degrees Celsius in darkness. One of the most extreme temperature ranges of any surface in the solar system, all happening on the doorstep of our own planet. But an airless, cratered, tidally locked moon slowly drifting away from Earth still leaves one enormous question unanswered. Because everything we've covered so far concerns the moon's surface and its orbit. What's actually happening underneath all that gray dust and ancient lava rock? That question is where this story gets genuinely strange. Here's the real question worth asking at this point. If the moon has no atmosphere, no active volcanoes, and looks from the outside like the most geologically dead object we could possibly study, is it actually dead all the way down? Or is something still happening deep inside it? You'd assume that after billions of years of cooling in the vacuum of space, the moon would have long since settled into a completely solid, silent, geologically inert ball of rock. That assumption held for decades. It's wrong. And the evidence for that comes from a set of instruments Apollo astronauts left behind on the lunar surface. Seismometers. Those instruments recorded something nobody fully expected. Moonquakes. Real measurable tremors rippling through the lunar interior. Recorded over the years, the equipment remained active. Some of these tremors are triggered by the constant gravitational tides from Earth, still tugging and flexing the moon's interior, the same way it once dragged our oceans into bulges. Others come from the extreme daily temperature swings we just covered, as the moon's crust expands and contracts violently between blistering day and frozen night, cracking and settling like an old house groaning as it cools. And some are triggered by the impacts of meteorites, striking the surface and sending shock waves rattling through the layers beneath. Picture a house made of stone left outside through a desert's baking days and freezing nights, year after year. Even with nothing living inside it, the stone itself keeps creaking, popping, and shifting from the sheer stress of the temperature swings alone. The moon, it turns out, is doing something remarkably similar, just on a planetary scale, and it has been groaning like this for billions of years. So if the moon is still shifting and settling, what does its interior actually look like? Here's where the layered structure gets genuinely interesting and genuinely small compared to what you'd expect. Like Earth, the moon is differentiated into distinct layers, a crust, a mantle, and a core. But unlike Earth's massive dominant core, the moon's core is proportionally tiny, a solid iron-rich inner sphere with a radius of only around 240 kilometers, wrapped in a thin shell of liquid iron roughly 90 kilometers thick. Surrounding that is a partially molten layer, and above that, a rocky mantle believed to be made largely of minerals like olivine and pyroxene. The same magnesium, iron, silicon, and oxygen-based building blocks found deep inside Earth itself. The outermost layer, the crust, isn't uniform either. It runs about 40 kilometers thick on the familiar near side, but swells to as much as 60 kilometers thick on the mysterious far side. A difference that connects directly back to the puzzle of why one hemisphere is covered in dark lava plains and the other isn't. You'd think a core this small, this cold, this ancient, couldn't possibly still be doing anything interesting. But the seismic data says otherwise. The presence of a genuinely molten layer, even a thin one, means the moon is not the fully dead world it's often described as in popular imagination. It's a slowly cooling ember, not a cold stone. For decades, after analyzing the rock samples brought back from every Apollo and Soviet Luna mission, scientists were confident about one thing. The moon was bone dry. No water, no ice, nothing. That conclusion held for over 30 years, until it was completely overturned. The first solid evidence of lunar water came from an orbital mission that detected hydroxyl molecules spread across the moon's surface, concentrated most heavily near the poles. Since then, missions studying the moon's permanently shadowed polar craters, regions so deep and so perfectly angled away from the sun that direct sunlight has never touched their floors, potentially for billions of years, confirmed something remarkable. Genuine deposits of water ice, frozen and preserved in some of the coldest, darkest, most permanently shadowed real estate anywhere in the solar system. It doesn't stop there. Researchers later discovered something even stranger. The moon appears to release trace amounts of water when it's struck by micrometeoroid impacts during meteor showers, with the shock of each strike vaporizing material and releasing water molecules that had been quietly bound to the grains of lunar soil. And in a finding that overturned assumptions yet again, infrared observations eventually confirmed water molecules, even in sunlit regions of the lunar surface, in craters far from the permanently shadowed poles, suggesting lunar water isn't confined to the frozen dark corners we originally assumed, but may be more widely distributed across the moon than anyone expected. Where did all this water actually come from? The leading explanation points to a combination of sources: ancient comet and asteroid impacts delivering ice directly, and a slower, ongoing chemical process where hydrogen ions carried by the solar wind react with oxygen already present in the lunar soil, quietly generating water molecules one atom at a time across billions of years of exposure. This single discovery, water, hiding in the last place anyone expected to find it, didn't just rewrite our understanding of the moon's chemistry. It rewrote our understanding of what the moon could become. Let's take everything we've covered to its most extreme, unsettling conclusion. Because the moon's slow drift away from Earth isn't just a curious footnote. It's a countdown clock on something you've almost certainly witnessed or hope to witness at least once in your life: a total solar eclipse. The reason total solar eclipses look the way they do, the moon fitting almost perfectly over the disk of the sun, revealing that ghostly ring of solar corona around a pitch-black center, comes down to a genuinely bizarre cosmic coincidence. The sun is about 400 times wider than the moon, but it also happens to sit roughly 400 times further away from Earth than the moon does. That ratio is what makes the sun and moon appear almost exactly the same size in our sky, allowing the smaller, closer moon to perfectly blot out the larger, more distant sun. But that perfect ratio only exists because of exactly how far away the moon currently happens to be. And the moon, as we've established, is drifting further away every single year. As that distance keeps growing, ever so slightly, the moon will keep appearing ever so slightly smaller in our sky, until eventually, roughly 600 million years from now, it will no longer be large enough to fully cover the sun's disk, even at the closest point in its orbit. Total solar eclipses, the kind that turn day briefly into night and reveal the sun's ghostly corona, will end. Every future eclipse from that point forward will be annular, a thin, blazing ring of sunlight surrounding a dark moon that simply isn't big enough anymore to finish the job. Think about the sheer scale of what that means. Every total solar eclipse ever witnessed by any human being in the entire history of our species. Every ancient civilization that built mythology around a vanishing sun. Every astronomer who has ever traveled across the globe chasing the path of totality. Everyone alive right now who has stood in a shadow, racing across the landscape at a kilometer per second. All of us are living inside a temporary, cosmically finite window. A window that opened only because Theia crashed into Earth 4.5 billion years ago at exactly the right angle, with exactly the right amount of debris, to create a moon of exactly the right size, at exactly the right distance, to produce this specific illusion in our sky. And that window is closing, one thumb's width of drift at a time, whether we're watching or not. So where does all of this leave us? Here's what we actually know, and why none of it should keep you up at night. But all of it should change the way you look at the moon the next time you see it. We know the moon was born from planetary violence, assembled from the wreckage of a collision so catastrophic it reshaped Earth itself. We know it's tidally locked to us, permanently showing one face while its far side quietly hides a completely different geological history, still not fully explained. We know it isn't the dead silent rock it appears to be. Its interior still groans and shifts from tides, temperature swings, and ancient impacts, recorded in real seismic data left behind by the astronauts who walked there. We know it's hiding genuine water ice in its coldest, darkest corners, and possibly scattered more widely than we ever expected. A discovery that quietly transformed the moon from a lifeless waypoint into a genuine resource for future human exploration. And we know, with complete scientific certainty, that it is drifting away from us, 3.8 centimeters at a time, on a trajectory that will eventually end one of the most spectacular natural phenomena Earth has ever produced. None of this happens on a timescale that affects you or your children, or likely humanity's presence on this planet at all. We're talking hundreds of millions of years before eclipses fully disappear. But that's exactly what makes it worth sitting with. The moon you see tonight is not a fixed, eternal fixture of our sky. It's a slowly evolving relationship between two worlds, still playing out the consequences of a collision that happened before either of them had finished forming. And every night you glance up at it, you're catching a single frame of a story that started 4.5 billion years ago and won't finish for hundreds of millions more. If this kind of deep dive into the mechanics of our universe is something you want more of, make sure you're subscribed, because we're only getting started uncovering what's hiding in plain sight above our heads. Next time you catch a full moon, take a second look. You're not just looking at a rock, you're watching a slow-motion goodbye that's been unfolding since before life on Earth even existed. I'll see you in the next one.